Well, good morning, good Saturday morning. I apologize for having to miss class yesterday. Starting to get better. Uh, what I'd like to do, though, for this lesson is to sort of take a step back and give an example. This comes from the homework for this week, and then we're going to then take a look at Stokes Theorem, which actually gets us into the next homework 14. So this is from homework 13, which we had the lecture on Wednesday over. Anyway, let's do an application together. So this actually, this is the one we want to do. This is from question or homework 13. We'll do that other one late in a little bit when we talk about Stokes Theorem. So we've got S is a surface, which is a parallelogram, and it's parameterized by this U and V parameters. So X is this component, this part. There's that Y component, and there's a Z component, and we're told the parameters Y and V, their limits of integration. So whenever we're integrating a function in x, y, and z over a surface, we have this equality that we could take that if we parameterize it, x, y, and z, right? ds, that's what that is. That we can that this calculates the same as if we were to take the parameters, and we'll take the limit of the parameters of u and v over the two dimensions, right? We take the function x, y, and z, and then I guess we put a parentheses here. We multiply all of that times the magnitude of the cross vectors of r sub u, r sub v, dA, the area, and the area is just going to be du dv. Again, we could do this in either order, but that's how we're going to go about and do it. So first of all, what is the function of our parameterized function? So r of uv. So the function we have is a vector of x, the x component, 3u plus v, the y component, sorry, I get these letters all confused, and the z component. So we've got that going. So what we need to get is these two vectors so we can take their cross product. So we get r of u, that's just going to be the coefficients in front of the u, so that's going to be 3, 2, and 3, everything in front of a u, so coefficients in front of the u. The r sub v is all the coefficients in front of the v, so the x component will be 1. The y component is -3. And the z component, there is no v value here. This is just like a constant, so it's 0. Now we need to take this cross product and then get its magnitude. And this may be the harder part. So r of u cross r of v. Remember, we can do this cross product is I, J, K. So we've got 3, 2, 3 for the u component, and for the v, we've got 1 minus 3, 0. When we do the cross product, the x component, or the I direction, right, is going to be the cross product 2 times 0 minus -3 times -3. So this is going to be equal to 0 minus negative 9. It's going to be positive 9, right? The j component, remember the k and the I get that cross, and sort of think that we're going around the circle. So we start with this 3 and we cross it with the I, so that's 3 times 1 is 3, and then we take and we're going to subtract off this 0 times 3, which is 0. So we get 3 in the middle. And then for the k component, we're just going to cross the I and the j. So that is 3 times negative 3, which gives us negative 9, minus 1 times 2, which is 2. So this becomes positive 9 vector, 3, and negative 11. Now, for up here in this formula, we need its magnitude. So for magnitude, we take the square root of the x component squared plus the y component squared plus the z component squared. Because could put parentheses around all of these, but with the negatives it's important that gets squared. So that's 81 plus 9 plus 121. Add those together, we get 211 and the square root. So that's what we have. So that's this part of the formula. We now need to get the formula, actually what I need in here. This is true, but since we're doing everything in terms of u and v, what we really want to do is this is of the parameterized formula function, right? So we're going to need that component. So let's put the pieces together. So for the parameterized, we start off with x. X is equal to this part plus y, which is equal to that part, plus z, which is equal to that part. So we're going to add all those items together. Okay, so let's switch back here. So we're going to get the integral over this domain. Let's go ahead and just stick with, should we do du first or dv? We could go either route. Let's maybe see what we end up with first. So the x part is 3u plus v. Plus, so that's this part. The y part, which is 2u minus 3v. So that's the y, plus z, which is 2 plus 3u. So that's this part, that's the function here. We multiply that by the cross product, which we've calculated here. And then that's the area. What I got looking here, okay, what are we going to get? We're going to get, when we add these together, we're going to get, let's just kind of pencil out a 3 plus 2 plus 3. So that's 3, 5, 8u. The v's we're going to get v minus 3v, so that's minus 2v plus 2. So that all simplifies down to just this. You know, we could really do it either way, u or v. these a little bit smaller, I guess we could start with a dv du. So we'll integrate with respect to v first, and v smaller in its limits, I guess, or some boundaries. It goes from 1 to 2, so maybe that will be a little bit easier, I guess. V's going, or sorry, u is going from 2 to 4, so that goes 2 to 4. So yeah, we might get larger numbers, so I think I would just do it that way. Let's go ahead and now just integrate this and we'll have our answer. Easy for me to say, right? So this inner one, let's go ahead, we're integrating from 1 to 2, 8u minus 2v plus 2. And as we do this, we can just sort of say, we could keep writing this in the back, the square root of 2, but it's just a constant, so we could also just say, hey, let's not worry about it. And then again, we do have this other integral, which we will do later. So, but we're focusing on the inner part. So we're going to integrate this, put this to the front, and then we're going dv and then du. So we're first going to focus on sort of just doing this inner part. We'll get that done, then we'll go to the next step. So we integrate this with respect to v. So remember this little, anyway, I'll move forward. 8u, when you integrate it, it's like a constant, so that's going to be 8u, and then it integrates to v, if we just had something. Also, this 2 is going to integrate just to 2v. We're integrating with respect to v. It's the hardest thing to keep focused right now. So we're integrating with respect to v. There we go. Now the middle part, that is going to be 2v squared, right? We're adding 1 to the exponent divided by 2, so those 2's cancel. So that's our integration. We're going to go from 1 to 2, and again, this is all an inner part here. And then on the outer part, we still have our du, our square root of 211, and our integration from 2 to 4. Okay, so we plug in our limits. 2 is at the upper end, and remember this is getting plugged in for v. So then we end up with, let's see, here we are. We're going to end up with, plug in the 2, so we get, and we're plugging in for v, 8 times 2u minus 2 squared plus 2 times 2 minus, we do the same thing, plugging in 1. Remember to put this parentheses because this negative has to distribute on through. We get 8u times 1 minus 1 squared plus 2 times 1. We still have this du out here. We still are integrating from 2 to 4, square root of 211. Okay. So it looks like we get 16u minus 4 plus 4. That's nice. That cancels it out, each other, right? Yeah, gone. And then we're going to get 8, and this negative I'm going to distribute as I go. Kind of thinking what's going on. So I get 8 times 1 is going to give me minus 8u. Negative and negative is a positive. 1 squared is 1. And then a negative and a positive is negative 2. So let's see what we end up with. We're ending up integrating from 2 to 4. Square root of 211. 16u minus 8u gives us 8u. So that takes care of those guys, and then we get a 1 minus, so that's a minus 1. And we still, so it simplifies out fairly nicely. We're doing good so far. And then now we just need to integrate this part. And maybe we'll go this way. So 8u integrates into 8u squared, right? 1 plus 1 is 2 over 2, so that's going to make that 4u squared. And then negative 1 integrates just as minus u to the first power. We're going to put in our boundaries of 2 to 4, and then again in the very front we've got our square root of 211. Okay, so this is 4u squared. Plug in our upper limit, so we get square root of 211. We get 4 times 4 squared minus 4. Then we're going to subtract the when we plug in the limit of 2. So that's 4 times 2 squared minus 2. So now it's all numerical. So let's see, 4 squared is 16 times 4. That's 64 minus 4. This is going to be 2 squared is 4. That's 4 times 4 is 16. So minus 16 and then a plus 2. So this is negative 20. And 64, so that's positive 44. Plus 2 should give us 40, right? Combine those two. I'm trying to be careful here. 44 plus 2 should give us 46. That's right, 46. So our final answer should be 46 square root of 211. All right. So that's a parameterized parallelogram that's been parameterized over a surface integral. An example of those, which I hadn't worked an example in class. So take a look at that, see if that's helpful in moving you forward. So now we're ready for a discussion of Stokes Theorem, which is a more general rule than Green's Theorem. Green's Theorem is a special case of Stokes Theorem, so we should see something that is somewhat familiar. Stokes Theorem is going to help us to calculate a particular integral using a equivalent form, an equivalent integration. So it's a higher dimensional version of Green's Theorem is what they state, and it's about really we've got a surface and we're going to get the double integral. So what Stokes Theorem is about, you see the little person walking around here in a counterclockwise manner. The region will always be onto their left. So C is the path, or a particular path around the curve, around the space that we're going to be doing. And then we've got these normal vectors, remember 90-degree vectors coming off of the surface. And these ones are shown with a positive orientation. Remember, going out, they were going sort of towards the origin. The inner side, on the other side, that would be a negative orientation. and the little person would be walking in the other direction. Okay, so this is our space curve, and what we're working to find with Stokes' theorem, the little guy walking around here, is we've got the positive orientation. Notice coming up. You walk around and see you're heading in the point in the direction, so you're heading in sort of the directions that in would be. So what we need for Stokes' theorem is we need an oriented piecewise smooth curve surface. That's what we've got. It's bounded by the curve, which we've got here, and we're going in a positive orientation. If all that's happening, then we have a vector field whose components have continuous partial derivatives on an open region in 3 space, and it contains this surface. Then what we find is that taking the vector field dotted with the dr, we can calculate this over the curve, so that's sort of a space integral. What we can do is we can take over the space, the curl of f dotted with the surface. Okay, so this is what we're going to focus on, and remember we've calculated the curl previously, so it just is a technique to make the calculations a little easier. Okay. Also, since if we take the vector field and dot it with the tangent vector, we're over the surface rather than the radius. And also the same thing happens with the curl. We can also dot it with the normal vector, and what we find is that the tangent component of f is equal to the surface integral over s of the normal component of the curl of f. So again, when we have a positively oriented boundary curve, we often write it as a partial of s. So Stokes' theorem can also be written in this form. And again, most of this is we're going to be asked for what's on the right side here. We're going to use the left side. We're going to use this curl calculation and go with this route here. Okay. To tie it in with Green's theorem, we can simplify it a bit. All 3 of these together, really, Green's theorem, Stokes' theorem, and the fundamental theorem of calculus are all related in that if we have a surface, a special case, where we're in the xy plane and we have an upward orientation, then our normal vector is the k vector. It's directly up in the z direction, and so we get the curl dotted with the vector in the z direction, right? The normal vector going straight up times its area. So it simplifies things a bit when we're talking about a surface, a flat surface in the xy plane. Okay, so we're going to take a look at this example and just see how it's applied. So we're asked to find this integral over the curve, the vector field f dotted with dr. So we're given the function, and we're given the curve itself, which is an intersection of this plane y plus z equals 2 with the cylinder x squared plus y squared equals 1. They've got the drawing here, and you can see the curve ends up being an ellipse, and it's got positive orientation if we do counterclockwise from above. So what we're going to do is work through this example. Got the copy here on a Word document to make it a little bit easier to go through. So using Stokes' theorem, remember we're going to back over here. What we're going to use is that this will be the integral of the curl of f dotted with ds. Over the surface. Okay, and so one of the first things we need to do is calculate what this curl of f is. So we do that. And remember it's a cross product of the partial of x, partial of y, and the partial of z. And then down here is going to be the vector field. So we get minus y squared x and z squared. So I'm taking them right here from the function itself. So let's calculate the curl, and again we do this with we're doing the cross product. So for the I component, we take a partial of y, and since z squared is a constant in this case, that becomes 0, minus x, the partial of z, and when our function is just x, that's also 0. So that's the first portion. To get the j portion, remember we go from k to I and sort of a wraparound. So we're taking the partial of z with y squared. Of course, y squared doesn't have any z in it, so that is 0. And then we subtract off z squared, again wrapping around this way, sort of thinking of it circularly. Partial of x with z, that's also 0. Okay, so nothing much has happened. Finally, when we get to the k component, we're going to take I and j. So we get the partial of x with x, well that's 1. And then we subtract negative y squared, the partial, so that's going to be negative 2y. Minus minus makes that a plus. And so we get 0, 0, and we end up with 1 plus 2y in the k direction. Or we could use it as the component, right? So that is the curl of f. It is a vector. And notice the x and y components of the vectors are 0. Okay. So we can actually choose any boundary curve that we want to use. The one that's going to be the most convenient is the elliptical region that has the boundary of y plus z equals 2. So using this as our boundary with this cylinder, that'll be the most effective one for us to use. Okay, sorry for the pause there, but so now the curl of f ds, so we got this integral, double integral of 1 plus 2y dA and we're going with the function of here y plus z equals 2, So we'll make z into another function, bring the y over. Y is equal to 2 minus y. Think of this as some function of g of x, y. And so what we're going to want to use here is polar coordinates. So y equals r sine theta, x equals r cosine theta, but there's no x's in here. And so then remembering when we make this switch to polar coordinates, the area that we're integrating over becomes r dr d theta. Plugging in for the y, we get 1 plus 2r sine theta. Our integration, since we are dealing with that elliptical, this intersection, theta is going to go from 0 to 2 pi, and r goes from 0 to 1 from the cylinder. So we first integrate with respect to r. We could just distribute this on through. So let's get r plus 2r squared sine theta integrate. R integrated becomes r squared over 2. R squared becomes r cubed, 2r cubed over 3. Sine theta just comes along as a constant. And we go from r equals 0 to 1. When you plug in 0 for r, these both become 0. We still got one more integration to do here. So zeros cancel out, then we get 1. If we put 1 in here, we get 1/2. So that's all that's going to be left there. Put in 1 here, we get 1 cubed, still 1. So we get 2 sine theta over 3, or 2/3 sine theta d theta. And now when we integrate, 1/2 becomes 1/2 theta. Integrating sine, we get cosine, 2/3. Actually, we get a negative, because negative cosine, take the derivatives, cosine, you get negative sine. And again, that goes from theta equals 0 to 2 pi. So let's plug in 0 first. This becomes 0. Cosine of 0 is 1, so that's minus 2/3. bottom end we get 0 minus 2/3. And when we plug in 2 pi, we'll get 1/2 times 2 pi. Plug in 2 pi for cosine, that's going to be 1. So that gives us minus 2/3. And so we get 2 pi divided by 2 is just pi. We get minus 2/3. A minus and a minus make up plus 2/3. Our final answer is just pi. Okay, so that's how we can use Stokes Theorem when asked for this f dot of dr. We can remember that that gives us that the curl of f dotted with the times the surface area. So that's one example we wanted to take a look at. The other one that we're going to take a look at gives us another, here we go, another example with a different type of surface. So we want to just remember when we're asked to find this, we can find over the surface area the curl of f dotted with the surface, the surface. Okay. So finding the curl of f first, and again here's our function. Up here it's this vector field. We're going over a triangular region, and let's see if we could, x is at 4, y is at 4, and z is at 4, so a three-dimensional triangular region. So first we want to find the curl of f, which again involves getting the gradient crossed with the vector itself. So to do that, we've got I, j, and k. We've got the partial of x, partial of y, and the partial of z. Take the I component, so down here we're going to have x squared plus y squared. We're going to take the j component, y squared plus z squared, and the k component, z squared plus x squared. So for the I component, this may get a little messy, alright? We're going to partial of y times of this part, there is no y, so that's going to give us a 0 to start off with, minus this part, the partial of z. Well, there is a z part, so that's going to be 2z minus 2z. I like to kind of do it this way. You could do it with vectors, but okay, so that's for the I component. The j component, again, we're going to go from the k to the I and kind of go, circularly around. So we take the partial of z with respect to here. So there is no z, so that part's going to be 0, minus this part. We're taking the partial of x, so that's going to be 2x. Finally, when we need the k component, we're going to go I to j. So partial of x, this first part is 0. Kind of the story is going that way. And then we take the partial, we're subtracting that part, and partial of y is going to be 2y. So this all becomes a vector of negative 2z, negative 2x, negative 2y. And that's our curl. Now what does our surface look like? It's triangular, going, it's a triangle formed by the vertices at these 3 points. What that shows us is that x could be 4, x really goes from 0 to 4, y goes from 0 to 4, z goes from 0 to 4. Okay, so we've got the equation that can represent it as x plus y plus z equals 4, and we can turn that into more functions, kind of turn z into this function of x and y by solving for z, so the x and y come over, so you end up with 4 minus x minus y. It's just another way to look at that equation, and we get the restrictions that since it's a triangle, x has to be greater than 0 because that's the smallest, y will be greater than 0, and then we let z has to be greater than this, that this part, which is z, also has to be greater than or equal to 0. Right, so x is greater than or equal to 0, y is greater than or equal to 0, and if we look at the boundaries, the maximum any of these can become is 4. Okay, so we can now integrate this with a double integral over this surface. And again, what we do is we take our vector that we've come up with, our curl, dotted with the s. So minus 2z I minus 2x j minus 2y k ds Okay, so now we're going to take the surface, we're going to make that into, do it over the domain of the 2 dimensions x and y. And so since the x component's negative, we get that coming off from here, minus negative 2z times the partial of g with respect to x, because that's the I component, and here's our g of x right here, and then we get a minus coming off because of the negative on the y, minus 2x, that's that component, times the partial of g with respect to y, and then since the z component is positive, we just get a plus the last component there. Okay, so let's go, the partial with respect to x, this is just going to be negative 1, so we've got a negative, negative, negative 1, this becomes negative 2z. Here, partial of y is going to be negative y, so we've got a negative, 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 and we end up with a negative 2x. And then finally, we just end up with negative 2y here. Lastly, since we're doing this with respect to x and y, we're going to plug in the value for z, which is 4 minus xy. So you get negative 2, 4 minus x minus y minus 2x minus 2y dA. And let's just distribute through, so we get negative 8, we get a positive 2x, positive 2y, and notice a negative 2x and negative 2y, so those all cancel out, leaving us with just the integration over the domain of negative 8 times dA. We could do this as dx dy and integrate over that surface, but that would just give us the area that's formed by the, and since we have a triangular region, the domain is going to be the projection of, here's the x coordinate at 4, the y coordinate at 4, so it's this triangle projected down onto the xy plane. So it's really just the area, this area times this constant. Okay, so what's this area going to be? Well, the area of this triangle is going to be 1/2 the base times the height, which is height 4 times 4, which is 16 over 2, which is 8. Right. So that's dA. That's our area, and then we just take that times negative 8. So negative 8 times the area, which is positive 8, gives us an answer of negative 64. So that is the answer to using Stokes' theorem to evaluate this vector field. And the answer for this over this curve. Okay, so that is our second example, and we'll follow up on Wednesday. What I'm going to do is I will work on the next section and post that early so that on Wednesday we can discuss any questions you may have.